Welcome back, physics fans and students in my Physics 100 class. Obviously, those are two completely separate groups. And physics cats. But not Charger's cat, because he may be dead, maybe alive, I don't know. Actually, he's both at the same time. That's where it is. So our goal for today is to understand magnetism and how magnetism allows us to be alive, as well as how it allows us to create, actually that's induction, that's the next lecture. And we're also going to learn how to build our own magnet. So our goals are to understand magnetism. Our objectives are to understand magnetic fields and magnetic lines very briefly. We understand why magnetic fields are important for the Earth and life on Earth. Basically, we wouldn't have life without it. We're going to understand magnetic force. This weird equation here, the one equation that we'll see, both in amount and direction. Those are two separate things. I've written direction on the board because that one's a little bit weird. We'll try to understand motions of motions of charges in a magnetic field, both ones that are perpendicular and parallel and hybrid. Then we'll learn quickly about magnetic domains and how that leads us to be able to build our own magnets at home. So just like with electric fields and gravitational fields, magnetic fields are an indicator of magnetic topography, magnetic heights, if you will. This is oftentimes illustrated with a dipole magnet. We have the north side and the south side. In the magnetic lines, which indicate where the magnetic fields are, go from the south to the north. By the way, fun fact, the Earth is actually backwards. Our north pole is actually a magnetic south, and our south pole is actually a magnetic north by this definition. And if you put metal, you can see that the metal, or ferrous magnetic metal, that's like iron bits, you can see that they align themselves with the magnetic field lines, and you can see where the magnetic field lines are. And much like electric fields are lines which charges will move along from high to low, magnetic field lines are also lines that the charges will stay close to. I'm doing a little bit of hand waving here, from one point to another. The reality, though, is magnetic fields or force barriers to charged particles. Kind of like the shields and force fields that you see in Star Trek and Star Wars. They're real, but they only work against charged particles. So that means if you find yourself in a futuristic war and someone shoots a laser gun, a plasma gun at you, a plasma gun would be a gun that shoots charged particles at close to the speed of light. The moment they reach for the trigger, you put up a magnetic field, the plasma will go around you, and you will be safe. Unless they throw the gun at you. The gun's not charged, so you're not safe. They just better hope that they knock you out, otherwise you will shoot them with their own plasma gun. And that'd be kind of embarrassing. So wars of the future. That's why in Star Trek and Star Wars, a lot of times they'll have multiple sets of weapons, plasma weapons, and just straight projectile weapons, because magnetic fields don't help against projectile weapons unless you can mass heat it suddenly and turn it into plasma and then deflect it. It's a little tough. Magnets usually have a north end and a south end. More on that later when we talk about magnetic domains. Kind of like you have positive and negative charges. You can read that. I think I've already covered that page pretty well. Our planet Earth has a magnetic field. We're going to learn about induction in the next lecture. And it turns out when you take charged particles, you move them in a circle, you induce a magnetic field. The Earth has a liquid iron core that rotates and convects, and between the two of those, we're not quite completely sure how much of it's from convection and how much of it's from rotation. We have moving particles, and that generates the magnetic field of the Earth. Now, this magnetic field of the Earth protects the Earth from charged particles, such as cosmic rays, and also pieces of the sun that are thrown off into space. Now, our sun is made of plasma, which means it's superheated gas. It's not actually gas, it's the fourth beta called plasma. So it's all charged particles. So when the sun throws off pieces of the sun into space, say during a solar flare, those pieces of the sun go hundreds of miles per second, and they're all charged. And they can run into the Earth and do lots of damage to our atmosphere, not to us on the surface, but to the atmosphere, unless we had a way to protect our atmosphere. We do, and that's what magnetic fields. So the magnetic fields mean that these charged particles hit our magnetic field and then go around the Earth and behind the Earth and keep on going. And this means that our atmosphere is largely protected, except for two holes at the North Pole and the South Pole, because we have fields that do this, and so there's two spots where there's a hole, and charged particles can go down in there, hit the atmosphere, break apart molecules, mostly oxygen. Those molecules come back together, and when they do, that's the aurora. Now, that's great and all. What does that mean about life on planet Earth? Well, it turns out to have life on the surface, now this doesn't mean anything, it doesn't say anything about life underneath the surface, but on the surface of a planet, you need to have magnetic fields. Without magnetic fields, when we look at our cousins, Venus and Mars, both don't have magnetic fields now. Venus, who knows if it ever did. Mars doesn't anymore because its core turned solid. Once it did so, its magnetic field went away. On both planets, and this has been confirmed for Mars using some of the probes we have around Mars. Solar winds hit the atmosphere, break the molecules apart. For Venus, it broke apart water molecules and dragged the hydrogen into space because Venus is not massive enough to keep its hydrogen. Well, this meant you ran out of hydrogen, and once you run out of hydrogen in water, that gets rid of most of the water. And in fact, Venus lost 99.99% of its water. Without that water, it couldn't form the oceans. Without the oceans, you couldn't get the carbon dioxide out of the atmosphere. On Earth, we got our carbon dioxide out by putting it into the deep ocean, where it's been for 4 billion years, and hopefully it will be for the next 1 billion or 2 billion years. And so we got it out of the atmosphere. Venus did not, so it has an atmosphere 90 times thicker than Earth's, made mostly carbon dioxide. And carbon dioxide is a greenhouse gas, which means it absorbs the planet's heat, and then sends that heat back to the planet. And so the surface of Venus is almost hot enough to melt lead. Actually, I think it is hot enough to melt lead, just barely. It's 700 degrees Kelvin. It's hotter than your oven by hundreds of degrees. And so that's a problem. You can't have life on Mars. Venus. It's just too hot. Mars is the opposite story. Mars, being an even smaller planet than Earth and Venus, when it broke apart carbon dioxide, the oxygen can be dragged into space, and so it lost almost its entire atmosphere. So it has an atmosphere 100 times thinner than the Earth's, and even though it's made of completely carbon dioxide, almost completely carbon dioxide, there's so little of it total that the greenhouse heating is only a few degrees, 10 degrees Fahrenheit, and so that means it's too cold. And in the past, it was warmer because it had more atmosphere, more greenhouse warming. It was a nice planet, but then it lost its atmosphere and became cold. It's still losing atmosphere today. We actually can measure the atmosphere being removed from Mars, so it's still losing atmosphere. Its atmosphere is continuing to get thinner and thinner, slowly with time. Because of that, the atmosphere is too thin. You can't have liquid water on the planet. I'm skipping over a couple steps there because this isn't that kind of class. But the point is, planets without a magnetic field either have an atmosphere that has too much carbon dioxide, way too much carbon dioxide, and be way too hot, or they'll have almost no atmosphere at all and be too cold and not be able to have enough atmospheric pressure to even have liquid water. Now, that second planet with very little atmosphere could still have life underneath the surface where it's warmer and you have pressure and you have liquid water, but not on the surface. So the fact that we live on the surface of Earth is due to the fact that we have a magnetic field. Now don't worry, if our magnetic field shut off for a few years, it wouldn't be enough time to get rid of our water. It would take about 50 to 100 million years for that to occur. So, we owe our lives to magnetic fields. Magnetic fields are important. We use them in other ways too. MRI machines is magnetic resonance. We use magnets in all sorts of places. Magnets are useful. So let's calculate the magnetic force. Now the direction of the force is very complicated. If you're in a trig or calculus-based or trig-based class, you would use the right-hand rule, where you have A, B, C, force, velocity, magnetic field. You have to orient your hand until each one's pointing in the direction that you want, and then the third one will point in whatever direction you're trying to solve for. Very complicated. If you're in a calculus-based class, you will use advanced mathematics to do it, matrices, and we definitely don't get into that here. So what I will say here is that the direction of the magnetic force is perpendicular to both the magnetic field and the velocity. And the magnetic field and velocity have to be perpendicular to each other, or at least have parts that are perpendicular to each other, otherwise there's no force at all. So if I have a magnetic field and a velocity, the force is in the third dimension, and I won't give you enough to be able to figure out whether it's this way or this way. That would involve too much. So just know it's perpendicular to both velocity and magnetic field. That's all we're going to do with direction of force. Now for the amount of force. This one is sort of straightforward except for that funny big X. So the magnetic force equals the charge times its velocity. This is a normal multiplication. X, the magnetic field. Now this big giant X is not a normal multiplication. Now those with advanced mathematics will recognize it for what it really is. I'm not going to say what it is because we don't do that much math. If the velocity and magnetic field are perfectly perpendicular, meaning they're 90 degrees apart, then the X is a normal multiplication. If the velocity is parallel to the field, then Vxb, by the way, magnetic field is denoted B. So that's where that B came from. Again, it comes to the Italian again. Vxb is 0 if they're parallel. So the only way you get a magnetic force is if the velocity has a part of its velocity that is perpendicular to the field. Now in the case where the velocity has components that are both perpendicular and parallel to the field, you ignore the parallel component and only look at the perpendicular component. And that's what you put in for the velocity. So for example, if my magnetic field is this way, and my velocity is this way, and I'm going to break this up and just put in numbers. Let's say, let's give a magnetic field of 5, and the units of magnetic field are Tesla. Let's say my velocity is 15 meters per second up, and 3 meters per second, I'm going to call this forward, just to put a direction. I ignore the part that is parallel, sorry. 15 is parallel to the 5, so I ignore this part. And I only consider the 3. And let's say my charge is 0.1 coulombs. I have a huge charge. My force would equal 0.1 coulombs, which is the charge, times the velocity. And I'm going to leave off the direction because we have to do the direction some other way. Times the 5 Tesla. Notice I only put the part that was perpendicular into the equation. The part that's parallel, we ignore it for the force. And this would be 1.5 newtons. Now, for the direction, it's perpendicular to the magnetic field and perpendicular to the velocity, and I'm ignoring this part because that part doesn't count. So it's perpendicular to this and perpendicular to that, and so the direction of the force would need to be this way, out of the board, or this way into the board, depending upon the sign of the charge. Yeah, basically the sign of the charge. I won't give you any more to that to be able to figure out which way is which, because in this class I'm not going to have you calculate that specifically. I just want you to say out of board or into board, or you can call this the Z direction, I guess, and this would be the Y and X direction. That's good enough for this class. So again, the direction of force is the axis that V and B do not use. That's the only way to get the direction, the axis of the direction of the force, which is the only thing we're going to do in this class. Okay. Hopefully that makes a little bit of sense. All right, no sample problem, well, no numeric sample problems here because it's all level 1. You just put in things and just make sure that these two are parts that are parallel, and you'll be fine. We'll do a little bit more of the numerics in recitation and in the homework section. All right, so now let's examine what the motions of objects are like in a magnetic field. So let's take the surface of the sun. So the ground, my floor is our surface of my sun, and let's say I have a prominence, which is a magnetic field that's poking down the surface of the sun. Let's say it's going straight up, and I'm a lonely electron going in this direction. And we're assuming a constant magnetic field. So I'm moving this way initially. Magnetic field's this way. Let's examine the force. What direction is the force going to be in? So think about that for a moment. So velocity, magnetic field. Now the force has to be perpendicular to both of them. So that means it's either this way or that way. Now for sake of me being in this room, I said it was an electron, but let's just say I'm a charged particle. We don't know whether I'm positive or negatively charged. And let's say because of my charge, my force is this way. Because if my force is this way, I'm going to run to the board. Now, I'm going this way. My force is this way. Now, what is my motion like? Do I make an immediate right turn and do this? Or do I do something else? Think about that for a moment. And remember Newton's first law. Okay, those who forgot, Newton's first law is an object motion stays in motion until acted upon by an outside force, and this applies to every dimension. So, moving this way, there's no force this way, so I'm going to keep moving that way. This is very similar to something else. If I throw the pin this way, there's no force in this direction, it keeps going this way, and there's a force downward. So what happens? It arcs. So I'm going to start to arc in this direction. Now, unlike the gravity scenario, where the force is always downwards, my direction of my force is going to change. Because now that I'm going from this way to this way, my force is always perpendicular to the direction of motion. So my force goes from being this way, as I rotate, to being this way. And so now I'm going to arc, and continue to arc, and continue to arc. And I'm in a small space, so it's kind of hard to do this properly. And what I'm going to end up doing is I'm going to make a circle around the magnetic field line. So charges that get thrown above the surface of the sun, but not enough to escape, circle around the magnetic field lines on their way back down to the surface of the sun. And that's why we get the prominences you see on the sun. Those are charges going back down to the surface of the sun along the magnetic field lines. That's why they make a loop, because the magnetic fields are a loop. All right. So that's for the motion we get if the velocity is perfectly perpendicular to the magnetic field. This also allows us to create cyclotrons, where we particle accelerators, if you will, where we make sure the magnetic field lines go one way and the velocities go another way, and they go in a loop. Now, what happens if the velocity of magnetic field's upwards and my velocity is also upwards? What's my motion like? Think about that for a moment. Well, in the direction of motion, the direction of the magnetic field, there's no force. So if I'm moving with the field, there's no force. I have a constant motion. I just go in a straight line and a constant velocity. Okay, so that's kind of a boring situation. Now, what about the real world? How often is it that an object moves perfectly perpendicular or perfectly parallel to a magnetic field? Probably not very often. So let's take the realistic case, that we have a velocity that has a component that's both vertical, or both perpendicular and parallel to my field, such as the one I drew up here before. So I have a magnetic field this way, and a velocity that goes both perpendicular and parallel to the field. What kind of motion will I get now? This one's a little bit tougher, because you have to consider each dimension separately. So the vertical dimension, in this case, since my magnetic field is vertical, is going to be constant. I mean, it's going to constantly move upwards. But in the plane, it's going to do a circle around the magnetic field line. So it's going to do a circle as it moves upwards at a constant velocity. So what kind of shape is that? Well, it's going to do this. It's going to spiral. So if I have my velocity perfectly perpendicular, I get a circle. If it's perfectly parallel, I get a straight line. And if it's both parallel and perpendicular, then I get a circle and a straight line, which means I get a spiral. All right, cyclotrons are devices that accelerate particles. They're particle accelerators that we humans use on purpose. And that's one use of the magnetic fields. All right, magnetic domains. Now suppose I had a lump of iron that was magnetized north and south. Now suppose I cut it in the middle. Straight down the middle. What's going to happen to my magnet? Will it, A, be completely destroyed? No more magnet. B, I'll have a north and a south piece that will want to attract each other. Or C, none of the above. Think about that for a moment. Pick A, B, or C. Come on, there's no D in this question. Why would you pick D? No, there's no E either. And no cat, there's no hairballs. Why would you pick hairball? Why do I let cats watch my videos? I don't understand. All right, the correct answer is none of the above. What will happen is you'll end up with two perfectly good magnets with north and south. Now, what we're looking at in a magnet is not one big giant bar. But really, if you look down small, it's all the atoms in most of the iron atoms, or some percentage of the iron atoms, are lined up in this direction. Now, reality is, you'll have some amount of randomness in the iron, where every atom and molecule will be aligned sort of differently. But more of them will be aligned this way, then we'll be aligned the other way, or aligned this way. And so the end result is that you get a net magnet. Kind of like we have the charges that move slightly more this way than that way, and that gives a current this way. Same thing works for magnetism. So if we cut the magnet in half, we still have little pieces of magnet that are still pointed that way and pointed that way, still pointing in the same direction, so we get that. So in order to magnetize something, which is where I'm going with this, all you have to do is find a way to line up those magnetic dipoles. So how do you do that? Well, you do it with electricity. So here's how you build your very own magnet. Warning, please use lower voltage batteries. Don't use a car battery to do this. You may hurt yourself. So, are you tired of losing screws back behind the couch or maybe into your power supply? Just magnetize your screwdriver. But how do we do that? Now first you have to make sure it is ferrous magnetic material, which means that a magnet has to be able to stick to it. So if your screwdriver is made of aluminum, which is not ferromagnetic, you can't turn it into a magnet, sorry. Magnets have to be able to stick to it. If a magnet will stick to it, then you can turn it into a magnet. So what you do is wrap a wire around the screwdriver as tightly as you can. The more coils you get, the stronger the magnet you'll create. Connect both ends to a power supply, such as just a couple of 8-volt batteries will be fine. You don't need anything too critically powerful. And just leave it on for a few hours. Come back, unhook the wires, take the wires off, and voila, you have a magnetic screwdriver of your very own. Not available in stores. Probably can sell it for more than a normal screwdriver. So a normal screwdriver, 25 cents. You can sell it for, I don't know, 50 cents. You just made some money. Well, maybe not, because the batteries are probably more expensive. So, no more dropping those pesky screws into there's as long as your screws are not made of aluminum. Then your magnet doesn't work on aluminum. So, oops. But that will magnetize your screwdriver. All right, so to wrap up, we've learned about magnetic fields and forces and why they're very important for us human beings to be alive. We learned about how charges move within these magnetic fields and the forces exerted on them. We discovered that magnetic fields, while seemingly boring, in fact, if you say magnetic field 3 times fast, you fall asleep. True story, you can try it at home. Try it after the video's over. They're not very important to the life on the surface of the Earth, and now we can build our own magnets. Hooray! And that's all for this lecture. Next lecture, induction. Which means I get to get out my interesting prop for that.